Hello and welcome. It's SFU Math 232, Brenda Davison. We're here, section 7.8, best approximation and least squares. So this is a major tool application of linear algebra, and we're going to talk a little bit about we're going to see how to do a linear regression using least squares, um, putting a putting the best line through a set of points when not all the points lie on the line. Okay, so we'll start here with the minimum distance problem. So I just want you to recall that what the norm of a vector is. The norm of a vector is the square root of the, this is the vector in R2, but it generalizes. So it's the square root of the sum of the squares of the components of the vector. All right, so if we have a subspace of Rn and a vector in Rn, and then we want to find the vector in the subspace that is closest to our vector that we chose. That is the distance. And how do we say closest? The distance between the vector and that we choose in W and the given vector in B is the smallest. Okay, let me just draw out an R2 example of this so we can see what this means. That vector is called the value of that vector, the norm of this vector. This guy here is the least squares error. So let's just see an R2 example. Okay, we have our axes. I'm going to make a subspace of R2. So here we are in R2. So I'm in R2. I'm going to make a subspace of R2, W. This subspace is a line through the origin. That's a subspace of R2. And we're going to say that. Subspace of R2. Okay, now what we do is we choose a vector B in R2. That vector can be anywhere. Here, there is B. Okay, now what I want to do is to try to find the vector in W that is closest to B. Okay, so let me just draw a couple of options here. Like, for example, I could choose this vector here, and I would then measure this distance. And that distance is this thing here. So I would so I could say I could choose W hat to be here, a vector in the subspace, and then I wonder, okay, is it how close is it to the vector B? I'm only allowed to choose vectors in W, and I want to know how close are they to the vector B. And I determine that closeness by calculating this distance here. Okay, so then I could I could try again. I could pick this guy here, my second attempt, and I'm like, oh, that the distance there, at least visually here, looks to be less. I could compute that, and then I could keep going like that, and I could pick W hat 3 here, and I would see it's like that, and then I could pick one out here, W hat 5, like that. I could pick one over here, W hat 6, and I would measure the distance. And then what I'm trying to do is see which W is closest based on calculating all of these distances and picking the one that is minimum. Okay, so I don't actually think that it's difficult to see in this two-dimensional example that this guy right here, this line right here, is the shortest. So that this then, of all the choices I could make, I should be picking this guy here as W hat. That would be the vector in W that is closest to B, and closest means that this distance here is minimum. Okay, so what is W hat? Well, W hat is in fact the projection of B onto W. And then I claim that if you choose W hat to be this guy here, then the distance between B and W hat is minimum. So then we would say here, W hat is the best approximation to B if we are forced to pick W hat from V. Okay. I believe in the textbook they have a 3D version of the same thing. So look at that one as well, and get into your head what we're trying to do, because I think that then makes this whole idea of the projection obvious. All right, so we're going to then state here a theorem. If W is a subspace of Rn, and B is a point in Rn, then there's a unique best approximation to B from W, namely W hat, the projection, sorry, I did this backwards. It's a projection onto W of B hat. Sorry about that, I wrote it backwards. Okay, so that is our best approximation. So how do I show this to be the case? Well, let's do it this way. I say take any W in the subspace, capital W, and then compute the distance between B and that W. That distance will be, well, let's look what that distance is. That is this, it is, we have here, well, let me just call this, let me just do it in black. So we take a W like that, and then we have this vector here as well. Okay, and the W, we can write that like this. B minus W is the B minus the projection onto W of B plus the projection of onto W of B minus W. Okay, basically here I'm adding 0, right? I've got here, this is equal to 0. So this is an add 0 statement. Okay, now, but the reason to do this is when we look at this, this version here, look at this vector right here. Considering this vector right here. This vector is in the complement of W. This vector here, the orthogonal complement of W. This vector here is in W. What does that mean? It means that those two blue boxed vectors are at right angles to one another. This guy and this guy are at right angles. So you can identify for yourself on that drawing, where is B minus the projection of B onto W, and where is the projection onto W of B minus W. I mean, both of these vectors here, both vectors are in W. So their difference is also going to be in W. Okay, now I'm going to take this statement here, this guy here, 1, and I'm going to apply the Pythagorean theorem to it. So I will deduce that the norm of B minus W squared is equal to the norm of B minus the projection W of B and the projection W to B minus W squared. Okay, I look at this term here. That term is non-zero and positive. I just want to reiterate, I can use this Pythagorean theorem because these two guys are orthogonal. These two guys here are orthogonal. Okay, this is this number right here is non-zero and positive. So that means if W is not equal to the projection, a slight G creeping in there, projection of B onto W, then we will have that the norm of B minus the projection of B onto W squared is, oh, I forgot a square there, is less than this guy here. That tells us then, directly means that W hat equal to the projection to W of B provides the minimum. Okay, so the fact that if it's not the projection, that this thing is non-zero and positive, leads us to the conclusion that this guy here is the minimum. Okay, let us start to set up an example which we won't actually conclude, but it'll bring up the issues that we want to discuss. Okay, so we have 4 data points here, and we want to fit them to a line. So we've decided in advance that whatever data, wherever this data came from, that we expect it to fit a linear model. So we've decided in advance that the model is linear. Now we've gone into a lab and we've measured something at these points. We measured at 1, we measured at 2, we measured at 3, and we measured at 4, and then we recorded our data. We got 2, 4, 6, and 7. And now we want to do is put a line through those points. Now clearly we only need 2 points to define a line. We've got 4. So this is an overdetermined system, and plus they don't all fit on the line. Okay, so for an exact fit, if you 2 points would do it. It would also be possible, for example, if this number here were 8, then I mean y equals 2x would capture them all. They would be all on the line. It would fit perfectly. But that number there is not 8, and they don't all fit on the line. So what is the best line to put through them? That's the question. So not all of these points fit on a single line. Okay, so which is the best line to use? Okay, and I have the line I want to fit it to. So now the problem becomes, so which is the best line to use? So that means what value of A and B should I choose? Okay, so let's look at it this way. We have y equals a plus bx, and I have this data point here, 1, 2. So let me just, I have a data point here, 1, 2. And so I'm thinking, okay, that means that 2 should be equal to a plus b times 1. Okay, and then also for the next data point, 2, 4, I should have that 4 is equal to a plus b times 2. Similarly for 6, well, let's do it this way. Similarly for 3, 6, I should have that 6 is equal to a plus b times 3. And for 4, 7, I should have that 7 is equal to a plus b times 4. Okay, what do we see here, folks? We see 4 equations and 2 unknowns. It's an overdetermined system. I've got equation 1, equation 2, equation 3, equation 4. I've got 4 equations and 2 unknowns. My unknowns here are A and B. Of course, we've been, this is where we rise to the challenge. We have been figuring out how to write this in a matrix vector way for this entire semester. So let me do that. This looks like this. 1, 1, 1, 2, 1, 3, 1, 4 times AB is equal to 2, 4, 6, and 7. Let's see if that works out. I'm looking for this first equation here. So I do this matrix vector multiplication. I see that 1 times A plus 1 times B is 2. And then similarly, I look here, the second row here, 1 times A plus 2 times B is equal to 4. So I've taken these 4 equations and put them into our matrix flavor. Now we could attempt to solve this normally, and we could try to solve this, and we could then potentially find values for A and B. So let's just set up to do that and then see what happens. We would write this in this manner here, the augmented matrix, and then we would row reduce like that. Let me just take row 2 minus row 1. And then row 3 minus row 1, and then row 4 minus row 1. Okay, and then we would stop here, and we would look here. I mean, these 3 things right here immediately tell us that this system is inconsistent. So if we didn't already notice that there's no possibility of fitting these 4 points onto a single line, we would now know this. It's inconsistent. So we can't just solve AX equals B and say, oh, there's your line. That's not working because it is not. There is no exact value of A and B which we can find in this manner that we're used to. Okay, so now we're going to stop this example right here. So now we're like, okay, so now we have a problem, but we don't want to just give up. We still want to find y equals a plus bx. We still want to find a and b. Now, how do we go about finding the best a and b? And what does it actually mean, best, anyways? Okay, so we're now going to stop this example. We're going to come back to it, and then we're going to talk about what to do to get an answer here when the system is inconsistent. And so the idea is that we will minimize the error. So we recognize that in our data there is some error, and so we will assume that there is some value of x. In this case here, our x was AB, right? There is some x that we can find that will be equal to b minus e, where e is some error vector. Okay, and ei is the error in the ith equation. So we're assuming now that the system is inconsistent, like we've just shown, and what we want to do is find an x that minimizes all of those errors. And how do we decide how to minimize the error? So there's a couple of possibilities that probably pop into your head right away. One is we could minimize the sum of the absolute values of the errors, or we could minimize the sum of the squares of the errors. So let's just take a graphical picture here. And I'm going to just mention a couple of things to be thinking about here. We're not going to spend too much time on this, but we've got, let us just think in a case where we've got, I don't know, 3 data points like this. I try to draw 3 data points where things look somewhat reasonable. And then I put a best fit line through them. Just there it is, like that. And I can see that these are the points that I measured at, x1, x2, and x3, and then these are the values that I measured in my lab. So I chose to measure at x1, and I recorded I recorded y1, and then I measured at x2, and I recorded y2, and I measured at x3, and I recorded y3. And each one of those measurements had an error, and the errors are visible here. So this one here, this distance right here is E1, and then this distance right here is E2, and then this distance right here is E3. And what we want to do is move this line, sort of rotate it up and down a little bit, move it however we like, in order to effect some minimization of the error. One option would be to attempt to minimize the absolute value of all of the errors. And then the other one is to minimize the squares of the errors. And what we are going to be doing is this guy here. We are doing least squares. This is why it's called least squares. Okay, we're going to try to minimize the square of the errors, the least squares approximation. And why are we doing that? So that's actually a bit of a difficult question, but I'm going to just provide a few little, just a minor amount of discussion about that. This is something that you could Google or look to, and it is a non sort of trivial question to decide exactly what does it mean to be best. What kind of error minimization are you going to do? So there's some things to consider. That this guy is in some sense more efficient, especially for us here in linear algebra, because you can capture the idea of the least squares in the norm of the error vector. You can't do that with this. So this one is somewhat more efficient, and I guess maybe easier might even be a better way. And there's actually another way we could think about the efficiency, and that is efficiency can mean this. How many samples do you need? How many samples for a given accuracy? So how many data points do you have to measure in order to ensure a certain accuracy of your fit? So that it is actually the case that the least squares provides for stated accuracy. You need less samples for the same accuracy. We're not going on to why that is. There's also questions about what does your underlying data look like. So there's questions here when you're making this choice about the structure of your underlying data. There may be reasons why you choose one method or other because you know something about the data that you're trying to measure. And this method here, what we're doing, we are assuming the errors are normally distributed. That may not be the case. And then you have to think more clearly about this. So there's that. There's a variety of things here. This would sometimes be called here the minimum absolute deviation. Minimum absolute deviation, and this one here, ordinary least squares. And that this is going to be us in B. Okay. Final thing I'm going to say about this is we could see that this for potentially for other purposes, this is a differentiable function where this is not. So that also can play into making your choice. Okay, that's enough said about this. If you're interested in that, there's a lot of literature on that. Meanwhile, what we're going to do is we're going to move on, and what we are going to do is minimize the sums of the squares of the error. Notice that by making that decision, we are emphasizing guys who have a lot of error. So if you have somebody way out here with large error, this point, that will impact the fit, where the line goes more than ones that are close because you're squaring it. Okay, so that it's not an equal weighting. Errors that are further from the fit line are weighted more heavily with this square method. So that's also something to bear in mind. Okay, we will notice then that the norm, we have this here, okay, and we'll notice that the norm of b minus ax is equal to e1 squared plus e2 squared plus ... plus en squared square root. Okay, and then what we're going to say is, well, I mean, if you minimize this, you also minimize. You also minimize this. Okay, the square root is an increasing function. Okay, and that is the least squares method. Okay, so that is where we're going with this. How do we do this? So now we're putting this guy to bed, and we are now going to go with this one forevermore. Okay, so we're going to do the least squares solution of linear systems. So we've got a matrix A, we've got a vector B, and then we want to find the vector in Rn that minimizes the norm of the errors. And that is our best approximate solution, or what we'll call our least square solution of Ax equals B. The value, this number, the norm of the difference between B and Ax hat, which is our best approximation, is called the least squares error. Now, we have that a couple of things to notice here. That is, when we choose any x in Rn, Ax is in the column space of A. Think of it as a linear combination. Ax is a linear combination of the columns of A. So finding the x hat that minimizes this guy here is equivalent to finding W hat here in the column space of the matrix where this guy is minimized. Okay, so that x hat satisfies this, that Ax is in the projection of B onto the column space. This is exactly what we saw in the first example, right? We said, okay, which W in W is closest to B? And we moved along the line and we said, oh, it's the W that is the projection of the vector onto the subspace. This is a restatement of that. Okay, I'm going to say a whole bunch of stuff here, and then we're going to come out with a formula, if you will, or a clear method of how to find out this vector x, which minimizes the error. So let us say a few things here. That is, the projection of B onto the column space of A is in the column space of A. I mean, you just projected it onto that. Okay. Therefore, Ax equal to the projection onto the column space of A of B is consistent, because we know that this vector here is in the column space of A. Okay. What can we immediately conclude from that? Every linear system Ax equals B has at least one least squares fit. Okay, when you go through this process, you are going to be able to find an answer. All right, now what I'm going to do is I'm going to take this guy here, right here, and I am going to go a B, take the vector B minus the left side of that equation, and then the vector B minus the right side. Projection onto the column space of A of B. Okay, now I'm going to multiply both sides by the transpose of A. Okay, that's multiplying both sides by A transpose. Now, I'm going to recall, in case we didn't just immediately recall this, I'm going to recall that the orthogonal complement of the column space is the null space of the transpose. Also, we will recall, we just saw earlier that B, the vector B, can be written as the sum of two vectors, one of which is a projection onto the column space, and the other which is a projection onto the orthogonal complement of the column space. Okay, that's just breaking out vector B into it's just like taking some vector B like this, and then breaking it out like this, B1 and B2. This, if you're, then your subspace is sort of assumed to be here. So you've got your projection, and then you've got your orthogonal complement. Okay, so you're just doing the vector decomposition like that. Okay. All right. So now though I've identified this little nugget right here, so I can rewrite this like this. That is the projection. I'm not changing this one here. And then this is going to change to the projection onto the null space of the transpose B. Okay, using this piece of information right here. Okay, now I'm going to just move one thing to the other side. So I'm just going to have B, and then I'm going to subtract the projection onto the column space of B from both sides, and that leaves me with this, the projection and the null space of A transpose of B. There it is. Okay, what does that tell me? It's pretty exciting, actually. It tells me that this vector right here is in the null space of A transpose. It's in the null space of A transpose. What does that mean? Well, if something's in the null space, what does it mean? It means if I take A transpose and multiply it by that vector, what am I going to get? Take A transpose, I multiply it by a vector which I know is in the null space. For sure, I'm going to get 0. Okay, now I have a what can I say next? A transpose times this thing is equal to 0. Therefore, A transpose times B minus AX is equal to 0. Then I can use some algebra, very basic algebra here. A transpose B is equal to A transpose A times X. And we can call this is the objective here. We can call this the normal. We will, I mean, no, we can. We do call this the normal equation, and we can solve the normal system exactly. It is the least squares solution to AX equals B. Okay, I recommend that I'm not going to ask you to rederive this equation on the final exam. I'm not going to do that. You may well be asked to use it, but I do think it's actually pretty valuable to go through this little derivation, also done in the textbook, very carefully. Because if you see how the vectors are being split up, where the projection is happening, why that's the minimum, why that's the least squares fit, it does mean that that you understanding the column space, the null space of the transpose, what is a projection, what is a subspace. Like, it does pull together quite a few ideas that if you go through this carefully and understand all of these steps, I think will bode well for you understanding many of the concepts. Meanwhile, once you do that, you're going to feel totally comfortable using this guy without wondering, I wonder why that miraculous little thing happens to be true. Okay, so let us see this now written here. The least squares solution to a linear system ax equals b are the exact solution. So the least squares solution to this guy is the exact solution to this guy. Okay. Normally, when we're doing this, this guy will be inconsistent. Otherwise, there's not much. If it's consistent, we can just get an exact solution. We don't need to do a least squares. So normally this guy will be inconsistent. And then what we want to do is get a least squares solution. And to do that, we simply solve this guy exactly. And if A has full column rank, then the A transpose A has an inverse, and we can simply write the solution, the least square solution we're looking for, on the left-hand side. And this is normally the case. If we have a least squares fit to a linear model, it will always have full column rank unless you measure twice at the same x value and get the same result and include both of them, which we don't normally do. Okay, so this is typical. Okay. All right, we're back to our original problem. We have 4 points. We have assumed a linear model. This is in advance. We're not trying to. We could assume a quadratic model or a cubic model. We could assume any model that we want, but then what we do is we want to take the data and fit it to our model. In this case, and it will be in any case that you see in this course, that we will assume a linear model. And we want to best fit this data, and because we're assuming a linear model, we call this linear regression. Okay, so from before, we know what the system looks like. It is looks like this: 1, 2, 3, 4, 1, 2, 3, 4. So you notice this we have here all ones in this column, and then what do we have in this column? The x data points, the x value of the data points. Put it that way, the x value of the data points. Okay, that is these guys here: 1, 2, 3, and 4. Okay, and then we have we're multiplying by some vector. I'm going to call it x here, but we know in this case we're looking for this. What's happening right here is this is ending up being called x1 and x2. Okay, x1 is going to be a and x2 is going to be b. So we're multiplying it by a vector x, x1 and x2. That's to be consistent with the normal equation above. So this guy here is the vector x. Okay, and then that is going to be equal to b. We already went through this earlier. That is 2, 4, 6, and 7. And you'll notice that these are the y data points, the y values of the data points. Not a bad idea to take your data points, your model, and set out the 4 equations with 4 unknowns and make sure you can figure out how to find A and how to find B. That's key to being able to employ this thing. Okay, A has full column rank here. Okay, you can see that no row is, well, you can see that, yeah, it has full column rank. There's no linear dependence. Okay, so I can proceed. Now I can proceed basically blindly in some sense. Having gone through the derivation and understanding why this works, all I have to do to find the least squares fit is make this calculation. I know what A is, I know what B is. Therefore, I know what A transpose is, and then I can take A transpose times A, I can take the inverse, I can multiply all these things together, and I get the answer. Okay? So you know, hitting into an exam, you have this pretty much. I would remember it like this. I find it easier to remember like that. But you have that in your head, and then you're able to employ it. So if you're you can sort of see the kind of thing where you try to solve ax equals b, you realize it's inconsistent, then maybe you want to after that be told or consider moving on to a least squares fit. Okay. All right, so let's do this example now and figure out what those numbers are. I've got A there, so I can get A transpose in short order. That is 1, 2, 3, 4. 1, 2, 3, 4. Okay. And then A transpose A, I multiply those two guys together. A times, oh, let me just write it. I'm going to multiply that by A, like that. And I get this guy here. I used Wolfram Alpha to do the calculations. So long as I didn't enter the numbers wrong, they should be correct. Okay, so I've multiplied A transpose A. Now I'm going to take the inverse, A transpose A inverse. And again, I entered that, this, not hard to calculate the inverse of that anyways, but you can enter it into computer system, or it's a 2x2 system. We can take the inverse quite quickly, and we get this. There it is. Okay, so now I'm making this calculation here. I basically managed to calculate this. I know what that is, and I know what that is. So now I'm going to do the multiplication of these three things together. So I'm computing x hat, our best fit, and that is A transpose A inverse times A transpose times B. And I write those things out. I got A transpose A inverse, that is 3 halves minus 1 half minus 1 half 1/5. I'm going to multiply that by A transpose, and I'm going to multiply that whole thing by B. Okay, I do that computation, and I find out that x hat is equal to 1 half and 17/10. So then I conclude that I had this here, y equals a plus bx. So I conclude that the best line through that data is y equals 1 half plus 1.7x. And none of the data points fit exactly onto the line, but it minimizes the error, the least squares error, of the sum of the squares of all the errors from each of the data points to the line of best fit. So I call this the least squares error best fit linear regression. Okay, so a major application of linear algebra to be able to do this, to do best fit of the data like this in the least squares model. Yeah, an important application. Okay, I'll be back with just 2 lectures after this, and then that will conclude our courses. So this one and 2 more. Thanks a lot, guys. Bye.